We're looking at alpha decay, so we have a nucleus that is decaying into an alpha particle and the remainder of the nucleus. Now the nucleus has mass big N and velocity big V. The alpha particle has mass little m and little v, and velocity little v. So let's answer this question. Write V in terms of big N, little m and little v. So if there are no external forces acting on the system, then there's conservation of momentum. Now the momentum of the nucleus is its mass, big N, times its velocity, big V. The momentum of the alpha particle is its mass times its velocity, so little m times little v. But because the alpha particle is moving in the opposite direction to the nucleus, put a minus sign here, and initially the nucleus has 0 momentum, so the total momentum of the system is 0, so we set that equal to 0. Now if we add mv to both sides, and divide by n, then we've answered the question. So big V is written entirely in terms of little v, m, and n. Now the next part of this question is asking what fraction of the total kinetic energy is contained within the alpha particle. So the total kinetic energy of the system is the kinetic energy of the nucleus, so E nucleus, plus the kinetic energy of the alpha particle. Equals E total. Now, what is the expression for this? Well, we know the expression for kinetic energy. It's a half times mass times velocity squared. Now we've got an expression for V, and we can square it. So V squared equals little m squared over big N squared times little v squared. So once we've done that, we can substitute that into this. So this is equal to a half n times m squared over big N squared times v squared. Cancel one of the n's, and then we have equals a half m squared over big N v squared, and you can spot that if we pull an m over n out of this, then this can be written as m over n times E alpha, where E alpha is a half little m little v squared. So if we substitute this into this expression, we get m over n times E alpha, that's E big N, plus E alpha, the energy of the alpha particle, equals E total. Now if we factor out E alpha, we see that this can be written as E alpha m over n plus 1. Now, if we put these over a common numerator, we can express this as E alpha times m plus big N over n equals E. So we want the fraction of the total kinetic energy that is contained within the alpha particle. So we divide by this factor here, and we get E alpha equals n over little n plus n times E. So that is the fraction of the total energy that's contained in the outer particle.